All right, I think I shared it. Can people see something title
Yeah,
slide there?
looks good.
Cool. Um, if anybody has questions while I'm talking, I guess just feel free to interrupt or maybe put it in the chat or anything. I don't mind. So stuff at NASA Atmosphere SIPs. I actually work at the University of Wisconsin at the Space Science and Engineering Center, and we do our work for NASA under a contract. Um, Most people probably don't know about us. I'm probably going to spend a few minutes talking about us. So we're founded in 1965, back in the era of satellite. When satellite remote sensing really took off, it actually started here. And the center has been involved in a lot of hardware over the years for instruments like Explorer 7, ATS-3, ground-based stuff like ARRI or scanning his, and actually one of the instruments on the Hubble was built in our building. Um, so we do hardware. We also do a lot of data validation, calibration, algorithm development for deriving products out of sensor data. There's studies in numerical weather prediction. We have the Cooperative Institute of Satellite Studies here. A little different is there's an ice core drilling team, but that does relate to the atmosphere because you can tell the atmosphere in the past based off of ice cores. But I work for a couple of very specific projects focused around data processing. The main one is the NASA Atmosphere SIPs. So there's two satellites in orbit, SNPP, NOAA 20, and there's another two planned in the coming years, JPSS2 in 2021, where we get basically the raw satellite data. We work with the science teams who develop algorithms to create different products. We work with them to refine their algorithms to work well in the HTC environment, and then we process the data, help them with any validation, and we send it to NASA in a forward stream manner. We also do kind of near real-time data, which is about as fast as you can get it from a polar orbiting satellite. Processed and delivered is a couple hours. So each of these satellites does about 14 polar orbits a day. That means it's basically going north to south constantly and collecting data. One of our other projects is also a NASA-funded one. It's collaboration with MIT. They're the main PIs for the project. Is Tropics, and that's a constellation of 6 CubeSats with passive microwave spectrometers on them. Those haven't launched yet. They're hopefully coming up in 2020 here. But that just adds it's much lower data volume than the other instruments, but it also adds, here's 6 more instruments that are constantly collecting, we're generating data for, and tracking the data and everything. So our data formats, they're called granules. They're usually time-based. On the right side here, we have an image of basically Spain, Western Europe, a bit of North Africa. That's 6 minutes of what the satellite sees as it's going overhead. We get data dumps at 2 points in the orbit, one over Svalbard, which is way to the north, and McMurdo from Antarctica. We receive this data, which is usually about 5 gigs each, and then it's up to us to deduplicate some of the data for like the near real-time stuff. For the more official data, that does come in nice 2-hour segments that we don't have to really deduplicate at all. So we split that data, and what we end up with is just under 90,000 files per year, per instrument, per product. So there's multiple instruments, many years of data. The first SMPP launched in 2011, and there's many products for every instrument, basically, for L2 or L3 or quick looks, whatever it be. So I guess the point of this slide is trying to say we have a lot of files. We have to keep track of all this. There's also other polar orbiting satellites that we have to collect data for science team validation. Like MODIS was the predecessor to the primary instrument we do now, so we keep a lot of that. We just finished ingesting some Calypso data, which is kind of a space-based LiDAR. We're also a couple other projects in the pipelines coming up. One that we're confirmed to be working for, another one that we're hopefully going to be working for. So we're growing pretty fast and we're staying busy. I threw this one in here because we're going to throw out some terms. Level 0, if you hear me say that, that's kind of raw data straight from, it's organized through a receiver. It's kind of organized a bit and then we receive it. L1 is like calibrated and geolocated, which you see at like the top right picture is that's an infrared band for L1. The top left picture is when you combine a few of those not infrared bands, when you combine a few L1 bands into like a normal RGB type image. And then the L2 products are where you get to the science algorithm derived information, such as like a cloud mask, aerosol optical thickness, cloud top heights, pretty much anything to do with the atmosphere. Level 3, I don't have a picture. That's just kind of a average put over a grid over a certain amount of time. NRT is near real time, and forward stream is just like this constant. These satellites are always collecting data, so it's a constant stream of data coming in every couple hours that we process and send back to NASA for distribution. So we have some requirements here. We're growing maybe about a petabyte a year. Before, we didn't have much data replication on Gluster. We had one small pool that was replicated, and that main pool wasn't. So we want something that gives us parity or replication. We also need to be able to handle 100 million plus objects. We want it to work well with HTC in general, preferably not POSIX. We like the object store method. We database all of our file information anyway, so object works well. It has to be good with programmatic data access because everything's automated in our system. Affordable, and hopefully it also works for VMs and Kubernetes. So data ingest and generation, here's some numbers I throw out here. In general, we ingest about just under 2 terabytes a day of that's a very normal day, which is approximately 30,000 objects a day in forward stream. What I'm trying to show in the pictures on the right here is that, the two different databases there, one's our ingest, one's our generation, is that the sizes vary greatly. Some days we ingest 4 terabytes because we're bulk ingesting. Other days we are the normal 500-600 gig. And pretty much the same with the forward stream processing or any bulk processing. Some days it's the normal 500 gig, terabyte, whatever. Other days, we can process up to 10 terabytes a day of data, or generating that much data per day and running for weeks at a time. So we prefer density over performance for our storage. Be anything from 6 to 12 terabyte disks. I have no plans to go greater than 12 terabyte disks because I don't want to have a decent amount of IOPS available from nearline SAS. We don't use any NVMe or SSDs in our cluster, but we do have a small pool of 10K SAS for hosting like RBDs and stuff for virtualization and Kubernetes. We split into two clusters. Probably talk as to why later, but our production cluster is kind of small, about 400 terabytes. Our archive cluster is the main one that's a little under 8 petabytes. There's a test cluster, that's just my playground, upgrades and whatnot. And we run using mostly Dell hardware, 24 OSDs a node, XFS. We don't do Blue Store yet, which I'll probably describe later why we don't do that. There's a specific reason. And mostly 20 gig networking for that. Now, one thing that we've kind of come to realize this year is we're an outlier. Most people are using the higher levels of Ceph, FFS, or the gateway pretty much. We use Gradle directly, and it seems to be we're a very small group of people who actually do this. We started this back in 2015, getting big into using Ceph or so. At the time, CephFS was a 3x replication, and we just straight up couldn't afford that. We also kind of assumed more people were using libradles because it's just so easy to utilize and so simple to utilize. So everything was kind of pointing towards making sense. Let's use libradles instead of the gateway for our object store. But when you do this, you end up having to build a bunch of necessary tools around libradles, and assuming that you just have objects. No good way of tracking it or anything like that. And for authentication, I mean, the gateway gives the ability through, the SD interface or Swift or whatever for a nice auth, but CephX auth and namespaces work well for us. So really, why not the gateway? Kind of just figured, why bother with another layer if it's not truly necessary? We don't require the advanced auth of that or anything. It's a very small subset of users that utilize our cluster. Really only a handful of people. We don't have scientists logging in or getting access to it directly. We're limited in our networking. We only have 10 gig switching. Once you have put gateways in front of it, everything goes through a gateway. Before, when we started this, we had 100 gigabits of compute. Now we have 200 gigabits of compute. So before, maybe a few gateways could have worked if you bonded it all together. But now, without 40 gig networking or whatever, getting the throughput getting it so you don't have a bottleneck on the throughput is a problem. And that's where you talk to libradles directly, you talk to the OSDs directly. There's no real easy bottleneck to create there. And kind of like I mentioned, the CephX works great for our use cases. We only have a few people. Everything's set up so that our apps usually have their own namespaces and a client keyring that access it. Everything's controlled via Puppet and Unix permissions for security of those key rings. Once again, there's only a few people who can actually log into like an SSH session. So it's fairly easy to manage all that. If there's a case where you're hundreds of users, that's probably more of a reason to go with the gateway instead of libradles. And then we have very few pools. It's mostly one big one per cluster, and then couple other pools for if we have overt or RBDs or stuff on there as well. So we had to build a whole bunch of stuff around this to work. We're a Python shop. We use the libradles Python bindings, and those work well, but it's not super easy to use all the time. So we wrote our own in-house library built around that called Gradle Lite. It's just an easier way to access all the Python bindings, put all the standard actions that you do with objects. We also added like a nice streamer object using Python buffered readers. The only problem that we've kind of run into this was our a pool alignment problem that was introduced due to some changes many versions ago. We got that fixed, and that was only because we were migrating pools. So we had old pools built from like the Hammer days, and a new pool built on like the Luminous date or something. And there's just a change in the defaults of what Ceph was doing that had to be addressed. And when we work with objects, we kind of just pass everything around using these URLs that basically define objects, where it follows like a standard URL syntax. We're encoding everything. Where in a single URL, you can say everything, where your user, a cluster, what pool, the keys, namespaces, objects. You can also define like the offset and sizes that you want to read from as well. So when you got like 100 million files or so, and help POSIX access to easily, troll through everything, you got to track it. So everything gets stored in multiple Postgres databases. But our primary one is one called dog. Every file gets its integrity checked every 2 months. This stuff hasn't really ever corrupted anything. Well, occasionally you get a bad block and something happens, but Ceph is able to repair that due to the erasure coding. But other than that, we've never had problems with this. And we also use a utility that keeps that data called PG track, so like an update in like an ingest database updates dog, which is the primary database of all the files. So if like a VOT, if it changes between what Ceph cluster or pool it's in, that moves. In addition to that, we also had a fused file system built on top of dog that kind of gave us a POSIX layer to Ceph with Gradle objects, which kind of sounds crazy. But it was really originally developed to make Gluster usable, since once you put a lot of files in Gluster, the directory listings fail most of the time and don't return in any reasonable amount of time. So it's just it also allowed us to, once we started using Ceph along with Gluster, there's a time there where we had both. We built Gradle support into it as well, and you're actually able to glue a file system together out of multiple different sources. So we actually had, a POSIX cluster and then libGradle's objects in a single POSIX file system that we can present to ourselves or science teams, whoever needed it. So this was just kind of built off of like a database and then these stub files which describe the object and the source, such as like the volume it's on in the database that it's aware of the object, and then just the basic information that you actually need to build a POSIX compliant object. This is kind of old. It's not the best technology, so we're trying to move away from that to dog v2. We want to completely get away from POSIX. So a better database schema, get rid of the fused file system, but the scientists and us, we do occasionally enjoy browsing the data. So we're coming up with a way where it's more of a Python API-based method of creating the HTTPD directory listings based off of like some assumptions of the data and the database. So basically, on the fly, it builds a file tree for you where the Gradle lice will fetch the object and give it back to you. So even more times we have to track our files here. Everything like an ingest and dog, that's all kind of hooked together via this PG track object where one object updates to the other. So we have this utility called CephDB where it's just constantly listing our pools and storing information, metadata in the database about it. It takes about 10 hours to list almost 97 million objects. This is something that just we run in our Kubernetes cluster. It's always there, always going. And we also use it to track, here's the actual state of stuff versus here's what we want it to be like. So we have some cleanup processes. Or if we remove it from a specific database, and then this sees it's removed, a process will notice, it'll do a diff and clean up the stuff to get rid of some of these extra files. But the really big advantage of this is that I keep mentioning how one database tends to update the other. This one's not updated by anything except for the process. So if somebody does a huge delete on accident and deletes an extra 50 million files that they weren't supposed to, or you fat finger the SQL query on an update or delete, we still have a spot of truth of here's what is in our Ceph cluster, and it makes it easier to recover that information. We do our backups, but it's always good to have the source of truth. And if you're going to be using libradles directly, I'd highly recommend something like this that is always not linked to anything and just the source of truth of here's what's in the Ceph cluster. One of the problems that we've had with libradles using it directly, there's really not too many problems we've actually run into, but a while back we had these big 5 gig files, and they get cut down to 6-minute smaller chunks of files for the level 2 or not the level 2, the level 1 processing. Well, when the file came in, it would kick off 20 jobs that would want to download this one big file and then split it up. That was a big problem where all of our jobs these should run in 15 minutes. They were taking 2 hours to finish. That's because Ceph just wasn't able to handle the requests of 20 jobs requesting the same 5 gig file at the same time, basically, and that single OSD was having a hard time rebuilding, fetching the pieces because it's erasure coded and rebuilding it and send it all out. So we had to develop a method to get around this. So we have this PDS server thing where it's another database that indexes our files into 1-minute chunks. And then this is where the reading from the size and offsets in the Radius Lite binary Python library comes in, so that once you query the database, I need starting this offset, this size of data. And now our jobs only download maybe 200 megabytes each of that level 0 data, and the problem doesn't really exist anymore. This is really only something that you'd probably experience in our situation here of using big objects in libradles. If you're using a gateway, it probably wouldn't be a problem because the objects are split into many different 4 meg chunks and across many OSDs and many PGs. So here I'm just trying to show a quick, you try to put it together. It's a complex system overview of kind of where we're actually reading and writing from Ceph. Once read many shop mostly. So we get our data in from Massa, we ingest it, we shove it into Ceph, and then on the left there, this is where having a laser pointer or something is handy. The PDS server there reads it in back from Ceph, indexes, and that's fine. And then way over on the right there, this flow process in the middle reads the data, sends it to our HT contour cluster, and jobs read the data from Ceph, and then they send back the products. And then when we deliver it again to Ceph, we do another read on it. We deliver to NASA, we do a read from Ceph as well. We do use some of the higher level functions of Ceph. Primarily the CephFS. We really don't do much with the gateway yet. Sometimes you just need POSIX, and there's this open source product from NASA called Worldview that we utilize for visualizing our data. We use it, the science teams use it, and you just need the POSIX layer there. So Cephfs and Kubernetes go together to create the persistent volumes in Kubernetes that serve some other apps where we just need the POSIX layer. So a while back, I did some testing of libgradles versus Cephfs out of curiosity, because now that Cephfs supports erasure coding via BlueStore backend. That's kind of awesome. So I was curious, like, what's the processing time differences? So if I run on one of our compute nodes a single granule, we would download the file into dev.shm and then process from there. So we try to, we don't rely on spinning disks really too much in iCluster. And on the left, we see pulling from Gradle directly into dev.shm. The middle one is using the PDS server into dev.shm. And the other one is doing it directly on Cephfs, processing that single granule from the level 0 to a level 1 product, basically. And in that case, Cephfs was slightly faster. These are in like 8.34 minutes. So then it's like, okay, let's try 100 granules on a 48 thread server, so 48 at a time. Obviously, the processing times are going to go up due to network contention. The CPU is just being running at 100%. But even then, we end up seeing, we got the Rados directly and dev.shm on the left there. But Cephfs is still very competitive. I did two different ones where we copied out of Cephfs into dev.shm and ran it, and the other one was running directly out of Cephfs, so the processing all happened there. And it's still very competitive. So I unleashed our entire cluster on it, about 2,400 cores running at the same time against Cephfs. We realized on the far right here there's a problem with this PDS fetch method that we use, so that can mostly be ignored. That's an outlier. But on the left here, you can see the Cephfs only was only 9 minutes, whereas the Cephfs dev.shm a little faster, about 30 seconds or so there. But it also still came in faster than our normal method of doing things with dev.shm. So the point I was trying to get across here, I suppose, is mostly that Cephfs, it's been production ready for some time now, for many versions, but it works very well when you just got 2,400, maybe even I've gone up to 2,800 jobs, banging on it at the same time, processing. It can work really well in the HTC environment, which, it kind of starts bringing the question of why don't we use Cephfs instead of the libgradles we're doing now. And that's something that we're kind of thinking about and considering as time goes forward. But we've built so much around what we're at right now. It wouldn't take too much effort, but it's enough to kind of put us off for the current time. So we've had some growing pains. This cluster started out as 5 nodes, 5 or 6 nodes, and maybe only half a petabyte, and now we're 50-some nodes and almost 8 petabytes with another one on the way here. So our early nodes, we had CPU memory problems per OSD and per terabyte. They were sized too small. We came from Gluster, and in Gluster you really didn't need too much memory or CPU to run it. Well, when in because of the nodes going down or things are happening, it takes CPU memory, and we learned had some painful times trying to learn that. Nowadays I just kind of oversize everything a bit. What's another stick of memory versus having problems? I'd rather just get that extra stick of memory. We've had 2.5, 3 full cluster outages. We had years ago, one was caused by a small relay by utilization that just kind of sent our cluster into a frenzy. I never got a good root cause of that. There must have been a bug somewhere with where the OSD maps were being regenerated too fast and the cluster wasn't keeping up. It was a couple day outage over the weekend there. I got it back up and running. 2018, we had a worse one. Well, this was kind of where we grew to the point that wasn't working too well for us anymore. The even worse part about this, it happened to mimic upgrade. So things were going great with the reboots and the upgrades and everything, and then I got to a node and I rebooted and everything just went to a mess. The OSD's thrashing, swapping, crashing all across the cluster. Multiple occasions we got things running mostly, but the big problem was that mons were constantly re-electing a quorum. The other tricky thing about this in the end was we ended up corrupting data across our cluster. Nodes would end up swapping and hanging, and I'd have to force reboot them. That was damaging blocks. But we did actually lose no data due to the erasure coding. Everything was recovered, and even then, there was only a few objects here or there that needed to be, fixed up a bit due to the corrupted blocks on, one or two nodes. In our future here, we're always trying to look for ways to be better, make things simpler. We're looking into this Pangeo product called ZAR. It's not really a product, it's an open source utility. If you work in geosciences, it's a different way of storing data where it's done more at the variable level instead of the file level. So you can reduce the amount of data volume that needs to be brought down to a host just by selecting I only want variables X, Y, and Z in this thing instead of the entire thing. And that it works directly with S3, so that means we could set up a Rados gateway and use it. It could also be kind of cool to get it to work directly with librados, but we'd have to kind of write our own driver for that. It's something we're looking into, and it seems the way that geosciences are kind of moving towards for data access. We'd love to move to BlueStore, but with BlueStore you can't use objects larger than 4 gigs. We do have objects that are 5, 6, 7 gigs. It's kind of the minority of the cluster, though. It's only about 160,000 objects and maybe 250 terabytes worth. But that is keeping us from moving to BlueStore. We've thought about maybe building striping into our Rados. We've also thought about using librados striper, but we'd have to write the Python bindings for that. I've mentioned that to some other people, and they kind of suggested that's not a great idea to use a striper, mostly because not many people use it. A handful from what I've seen, and even less in like the HTC environment like us. But when you boil it down, is it better to roll our own method of, striping into Rados Lite, or is it better to just use the librados striper where there's actually a couple other people that I know using it and it's lightly supported? The other big issue is our big cluster is stuck on the bobtail tunables. A weird thing was it was, built on Hammer, so I'm not sure why it wasn't using, I believe, the Firefly tunables back then. I'm preparing to get this up to optimal. It's just going to be a matter of making that change, and the cluster, everything's going to move on the cluster. It's preparing for that. There's some interesting ways of using the upmap. CERN has a script that can be used to, you make your change and then use the up mapping to basically stop everything and then slowly balance the changes in over time. Problem with that is we have some Joule clients, and UpNet requires Luminous, so that needs to be addressed before it can happen. We're also looking to use the X adders in Ceph. It is actually recently implemented from the last time I talked about the slide, so I crossed off one of those. Just basic stuff of storing the checksum with objects. So when Rados writes an object, does the put operation, it always stores the checksum at that time. And then we have the checksum in the databases as well. It's just another place to store some metadata, and we want to make better use of this. And as I mentioned before, we want to get the intelligent API instead of a fused file system. That's about it. A pretty slide of our core technologies in use. Ceph is a huge one, so is HT Condor. And then just everything, we rely on open source to run, and this is how we do it. So any questions, comments, thoughts? Brian asked, what's the erasure coding config in the chat? We're using 6+2. We first started, we did a 4+1 due to we only had 5 or 6 nodes in the cluster and couldn't really afford to do more at the time. So we had to do a big migration at one point of a few petabytes of data from one pool to the other to be on 6+2. Anybody else? Seems not. I guess thanks for joining. If you think of anything in the future, the slides and everything's recorded. I'm easy enough to find online to contact. Just Google me. Thanks for joining.
Thanks very much, Kevin. Have a good day, everybody.